Hello and welcome to this video lecture and a simulation example for our SCRs and SCR Silicon Controlled Resistor. And for this video I will be showing you a basic example of how to operate an SCR, and we will go through the different parameters of SCR, especially on the gate voltage, the trigger voltage, the gate trigger voltage, and the holding current, and the output current of our SCR. And we will look into different scenarios on how to use the SCR, and how I will also be showing you how to turn off the SCR after it has been triggered. And yes, in this video I will be showing you a simulation, and we will basically play with our silicon controlled resistor. So see you on our simulation coming right up. Okay, so we are now at our multi-sim simulator, and we will now try to simulate SCR. So Control W, and we'll find the SCR if we type the component name SCR. So this is a generic simplified SCR thyristor for system simulation. So this is not based on real device, but it is an approximation of the behavior of a typical SCR. Okay, so and let's put it in our worksheet. And we'll also need some resistors, maybe 2 resistors, and another resistor which is a variable resistor. 1K is good. And we'll also have basic sources, DC power. Okay, we'll have 2 DC power for this case, and I think that's enough for this example. Okay, so let's position them. Let us say we have a 100 ohm load. That's assuming that we have a load, and that's what we are controlling. And we have the control for our gate. Let's make this 1 kilo ohm. Okay, so and we have our input voltage to the gate. Let's connect everything. Yes. Put some ground. Name this here as PG, so that we could use those naming later on when we try to measure. No, cancel. This is V. No, that's wrong. Here, maybe let's just put this probe 1. We have another probe here. Font, let's make it bigger. No, that's wrong. Here. There. Let's make it around 22, so that we could easily see them. Okay. Maybe we could hide the name. let's see this one. Before, let's hide drive this, apply. Okay. So we would see here parameters like what's very important for us here is the voltage, the VDC. In this case, we would want the VDC and the IDC. Okay, so we would have here the value of the current along the gate. I mean the gate along the SCR, and this one the current and the voltage that is going through our gate. Okay, let's try if we can remove some elements there. Yes, let's try removing this one, this one, this one, this one, so that we'll have let's just leave that as yes. Okay, no, 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 apply. Yeah, so we have a cleaner interface here. This one also. No, 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 yes, no, no, yes, no, no, no. Apply. Okay. Mm-hmm. I forgot about the voltage. Cancel. Uh, Voltage there, yes. Mm-hmm. So, in this case, let's start with 0%, assuming we have that, and we would assume that we have 0 volts here. And let's try to simulate this and see what is the behavior with this setup. We have here approximately 0 volts at the gate, and we know that at 0 volts we would assume that there is no current flowing, and we will expect the output current to be the least possible value in this scenario. Okay, so what we have here is current of at the output we have 2.4 microampere current, and we have 12 volts VDC measured at our SCR. So if we can measure 12 volts here, we would really assume that this is acting like an open circuit. Okay, so to make this interface a bit cleaner, so let's remove some elements again. Probably let's remove that and that so that we could only have two. This one also, remove that and remove that. We could only have two so that we can focus here. Okay. Mm-hmm. Mm-hmm. There. Okay, so that's better. So now let us try to increase the value of our gate voltage, because in this case it is only 120 microvolts, and our trigger voltage according to this is 2.5 volts. Okay, so let's try increasing the value. So from 120 microvolts, let's add a few percentage in here. Say 5%. We reached 571 millivolts, so that's not enough to turn on our the SCR. Okay, we have 10, so we have 1 volt, 10% of 1 kilo ohms, and we did not turn on the SCR because we would expect that it would only turn on at around 2.5 volts. So 20%, we have 2 volts. Still, the current is still very small. Okay, and 40, let's say around, well, we had at 40 earlier. So when we reached 40, we have 3.43. That's more than our trigger voltage. Of course, it will trigger on, and we would see here we have 120 milliampere. So assuming that the SCR will act as an open, I mean as a closed switch with very minimal resistance at its conduction mode. Okay, so we would expect that the current flowing through the SCR will be calculated as the voltage supply divided by the value of the resistance in series with our SCR, which is 100 ohms. And we would expect we'll have 0.12 ampere or 120 milliampere, which is very correct in this case. So we have now verified that if we increase the value of our gate to a value that is more than, or probably will slightly more than our trigger gate voltage, it will trigger our SCR to turn on. Okay, so let's try decreasing the value of our gate to the value that is less than the trigger voltage, and let's see what will happen. So right now we are at around 2.77, which is greater than the value of our trigger voltage. We are still maintaining the 120 milliampere, which is the on current in this setup. Okay, let's try decreasing this one. Okay, we are now less than the value of 2.5 trigger voltage, and we are still conducting in our SCR. Decreasing again, decreasing again. We have decreased to 1.57, and still we are on. Decreasing again, still on. The SCR is still on. Okay, so we need to remember that our SCR will stay on, okay, even if we decrease our gate voltage to the level below our trigger voltage. As long as it is triggered once, it will stay on. The SCR will stay on as long as it has maintained, or it has received the value of current more than its holding current. Okay, so it will hold its state once it is triggered if it has received the current more than the holding current. Okay, so that is the behavior of our SCR. So let us take note in this case that the holding current is, where's the values? SCR there. The holding current is 10 milliampere. So if we try to make this resistor as 100,200 milliampere and we turn it on, we would have 10 milliampere of current, which is the holding current exactly. Okay, yeah. So in this case, let's try starting at 0. Okay, so at 0, still no triggering because this is a very small current. At around 15%, 1.57 volts is the gate voltage, no triggering again. If we increase it to 35, we are 3.11 or 3.11, and we are now at the conduction mode of our SCR. Take note that this is the minimum holding current, so which would probably mean that if we decrease the value of our gate voltage, it might probably turn off because this is right at the border. Okay, right of the border of our holding current. So let's try. Yeah, and we are correct. The value of our current at the output side decreased to the level that is considered off. And yeah, if we maintain a current that is very near our holding current, it will not be able to hold its state. But if we increase the current, and then increase the voltage at the gate, triggering it once, and then returning to 0 at the gate, okay, we will see that our SCR is holding its previous state because it was initially triggered once, and it has a holding current, a current that is more than the holding current. Okay, so that is the behavior of our SCR, and we need to remember that one, that we cannot turn it off if we are maintaining a current that is more than the holding current. So in applications for SCRs, it would make sense that the value of the current flowing through the SCR is greater than the holding current, because SCRs are designed to be used for applications that would require high power, and thus it would require high current values. Okay, so in this case, again, we need to remember that once triggered, it will stay on its conduction state, and it will not turn off until we turn off the supply for the anode part, or the output part of our circuit. Okay, now if we would want to turn off our what you call that, if we would want to turn off the output, in this case, let's try putting an LED so that we could visualize what is on and what is off. Okay, so let's try looking for an LED, all groups, LED. Let's try maybe red. Okay, so that we could see what is on and what is off. And let's try if this circuit will make it turn on. So minimum requirement for LED is around 20 milliampere. Maybe it will turn it off on. Okay, so we are at 0%. Of course, it is expected to be off in this case. Off because of 2 volts, and on. Okay, so we are turned on because we have triggered it once, and because the holding current is more than the current is more than the holding current, it maintained the on state. So there's no way we could turn it off if we just use our gate trigger voltage. So in this case, we could use two methods of um, turning off our circuit, the output part of our circuit. Okay, and for that, we will be moving on to part 2 of our simulation, and that will be on the next video. So see you on the next video. Hi, and welcome to the continuation of our simulation. And again, as I've promised, we will be uh, showing how to turn off the SCR when it was once triggered. In this case, this is where we left off on part 1. And as a review, we could remember that in order to turn off the SCR, we have two known methods. First method is anode current interruption. That would mean we remove the current flowing through our anode, and we also have forced commutation. So I think the easier to show here is our anode current interruption. So we'll do that in this example. Okay. So in order to do anode current interruption, we would want to either cut off the current flowing through the anode, or divert that current in order for it not to flow on the anode. So let's try diversion first. So in order to divert, let's just put a switch, maybe SPST. Let's try this normally open. Okay, so for the diversion, we would want the current to flow directly to the ground so that it would not want to flow through the SCR. Okay, so in this case we will bypass it, and so that we could turn it off. Okay, let's try this one. I hope it works. I have not tried it earlier. So yeah, let's go. And right now we are turned off. The LED is turned off because this is the start of our simulation, and we have not supplied a trigger voltage. So when we trigger it to more than the 2.5 volts trigger voltage, the LED will turn on. And again, the behavior is once turned on, it will not turn off. So in order to turn it off, we will, according to our knowledge, we will do the the current interruption. So let's try. In this case, the current at the SCR is less. Okay, it became 8.15 picoampere, uh, greatly showing that we have been able to divert the current that is flowing through our SCR, and we know now that the value of current IDC is less than the holding current, so it must turn off in this case. If we remove the switch here, let's try to see if it will turn off. And yes, it did turn off. Okay, so we have successfully interrupted the current, and we have successfully turned off the latching effect of our SCR. So again, let's try that again. So not triggered, and let's trigger. So we have on, and even if we decrease the gate voltage, it will not turn off. So we use the forced current interruption, and when we remove that, we will see the effect. There, we have turned off the circuit. Okay, and that's it. Okay, let's try triggering it and then using the forced the interruption. So it turned off, and let's try turning it off now. And yeah, it still turned off. And okay, so that is the anode current interruption. Okay, so that's one of the two methods known to turn off the SCR. Okay, so that's it for part 2, and I will not show you the forced commutation. That would be for you to find out and for you to study on. And yeah, so good luck, and I hope you learned something today.